the states simplify dramatically and take a factorized form where the factors are related to the Q functions. And it would be amazing if we could find this simplifying basis in n equals 4, but this looks like a very hard problem because essentially we don't have a precise definition of what is the underlying integrable system at finite coupling. But still, there are some possibilities for trying to build a bridge between correlation functions and Q functions. One possibility, as we learned in a talk yesterday by Benjamin, is to try to understand the wrapping in the hexagon formalism, which is a systematic way to build correlators. And as he explained, wrapping should be encoded into using the TBA Y functions as building blocks. And we know that there is a way to link the Y functions and Q functions. So this could be a bridge. Another possibility that I discussed today is to study double scaling deformation of n equals 4, which is called the fishnet limit, where miraculously integrability becomes really crystal clear. And there is a hope of literally understanding a separation of variable and deriving these expressions for correlators in terms of Q functions. So the arrows don't work for changing the slides. Sorry. Okay, I'll do it like this. So in this double scaling limit defined by Gurdogan and Kazakov, what remains is that only two complex scalar fields remain interacting. They interact with these extremely simple Feynman rules. And the result is that only the diagrams that have a very regular structure with in the bulk some regular square lattice or fishnet are possible, and we would like to study correlation functions built out of these fishnets. And it was realized by Gromov and Sever that it's very useful to use look at an object that they call the CFT wave function, which essentially gives a realization of the operator state correspondence, but directly on the space of a spin chain. And it's defined in this way. This is a non-perturbative correlation function between a single trace operator and another trace of scalars that are evaluated at different points. And formally, it's given by the sum of infinitely many diagrams like this after renormalization. And the strategy is to look at these external legs of the correlator as sides of the spin chain. Each side will carry an infinite dimensional representation of the 4D conformal group, which is realized by the usual differential generator for scalars. And these wave functions encode the properties of the operators, such as the scaling dimension that can be extracted by acting with dilatations on the external legs. And amazingly, it's also an eigenstate of an integrable Hamiltonian. So there is this Hamiltonian equation, which follows from the iterative structure of these diagrams. And, and where the Hamiltonian is a differential operator that can be defined as the inverse of the operator that adds one wheel to the graph. And remarkably, this Hamiltonian is integrable. It can be embedded into a family of commuting transfer matrices. The transfer matrices that are relevant for today were built by the same authors, and they are the ones that have a finite dimensional representation in the auxiliary space. So here it's again representations of the 4D conformal group identified with SL4. And these representations are indicated by, yeah, please. So by these labels that denote the dimension. I see that there is a question. Okay. And so these transfer matrices are polynomials in the spectral parameter. They commute, so therefore the coefficients of the polynomial generate commuting integrals of motion, and their number is 4 times j, where j is the length of the spin chain, and it's believed that they are a complete description of the state, and one of them is the Hamiltonian itself. And the last bit of this slide, I also introduced for the experts in integrability, the usual inhomogeneities and twists, which are some useful regularization parameters. Yeah, please.
Just a confusion on the Hamiltonian. If you go back, the Hamiltonian basically removes one of these things. So is it only this eigenvalue equation? Is it only if you have an infinitely long object?
As for finite length.
How can it be an eigenvalue equation? I mean, if you remove one of these rings, you don't have the same state before and after.
Because it's after renormalization, so there is an infinite constant for multiplicative renormalization, so the discrete bit that you left behind is eliminated.
All right, thanks.
And so we've seen that we have all the structures of integrability in spin chains, like the one that Ruben explained yesterday. But the one that's missing here is the beta answers, because we don't have a good reference state to use. And so to find the spectrum, we need to use another method. A more general method is the method of TQ equations. And luckily, in the paradigm of integrability, we know that for models based on this SL4 symmetry, these TQ equations have a universal form, which is given here. So it's a finite difference equation for the Q function, where D is the shift operator in the spectral parameter, and these coefficients are the eigenvalues of the transfer matrices, which contain the integrals of motion. In the case of the fishnet model, concretely, we find this equation, and these terms in red contain these integrals of motion, which in particular include the coupling constant of the theory and also the scaling dimension of the operator. We can consider them as some variational parameters, and to find physical solutions, we need to impose a quantization condition. And to describe it, we need to look at the analytic properties of these Q functions. So in contrast with models solvable by beta ansatz, here the Q functions have infinitely many poles, and there are two independent bases of solutions of this TQ equation. One basis is 4 Q functions that have poles in the lower half plane, and the other basis have poles in the upper half plane. Because they solve the same finite difference equation, they must be related by a matrix which is aperiodic, this omega, which would be important also later. And the quantization condition is a condition for some zeros of this omega. Imposing this, one can compute numerically the spectrum for arbitrary precision. So now that we know how to compute the spectrum, because we didn't have the beta ansatz, we don't know the form of the eigenvectors. But I want to convince you that we should still care about the eigenvectors. And the reason is that they are very natural building blocks for the correlation functions. For example, if we look at this 3-point function, there is a way to decompose it, cutting in this way, which is a different way of cutting the one that is used usually in the hexagon formalism. But the advantage is that if we cut in this way in the fishnet model, all the coupling dependence can be put together with the wave functions. And in the middle, there is always a three-level graph that doesn't depend on the coupling. So if we were able to compute the wave functions, at least in principle, we reduce every correlation function to compute in a finite dimensional integral. And therefore, it's interesting to try to use SOV to determine precisely the form of these eigenvectors. So with this motivation, I now go to discussing SOV, and I want to distinguish two different approaches. One is the operatorial approach, and its goal is to find a good explicit description of the SOV basis and use it to determine the form of the factorization of the eigenstates into Q functions. And this follows the paradigm introduced for Slianin for SL2 models, where this basis is built as eigenstates of a certain B operator constructed out of the monodromy matrix. And this has never been achieved for a model as complicated as the fishnet theory, but there is at least a clear paradigm and some exciting developments in recent years for higher rank models. In particular, the form of this B operator is known at any rank and was found in these works in the first line. And there are also developments for setups very close to ours, such as SOV for fishnet graphs with open boundary conditions, which are related to the evaluation of Basso-Dixon fishnet integrals, and also developments for 2D versions of the fishnet model. And the other approach that I'll discuss today is called the functional approach. And the goal is different. It's to try to understand things about the fabrics of SOV in the model using only the TQ equation. And one of the main goals is to find the form in terms of SOV of the essentially the scalar products, or equivalently two-point functions. This is related to determining an important element, which is called the SOV measure. And this was determined for the first time for higher rank models using this functional approach, and it was not possible with operatorial methods alone. So I now discuss this problem. So we want to express these scalar products in terms of Q functions, and the strategy is to notice that the scalar products have many constraints. So between two different eigenstates of an integral model, so they should be orthogonal. So now let's assume SOV. So the states factorized into Q functions. And we use these two factorizing bases, X and Y, which satisfy some completeness relation. And we've learned in recent works that we should use two different bases to factorize the right and left states. And this implies in particular that this factor here, which is called the SFV measure, is a non-diagonal matrix. And this is an important element of the integrable structure. If we use this completeness relation, we should find that the scalar product is rewritten as some combination of Q functions formally of this form. And the challenge is to find such an expression that satisfies all these infinitely many constraints of orthogonality. And this would give information indirectly on this SOV measure. So to do this, in the next two slides, I introduce some technical ingredients. And the first one is that in this method, we need to use, in addition to the Baxter equation, also a dual Baxter equation, which is satisfied by some dual Q functions, which are built as 3x3 determinants of the original ones. The dual Baxter equation formally is obtained by interchanging the integrals of motion for the fundamental and anti-fundamental representation. And I will denote these two equations by some finite difference operators denoted as B and B dual. And it's also important to introduce a bilinear form pairing functions of the spectral parameter. So it works as an integral over some infinite vertical contour with some arbitrary aperiodic function mu, measure mu. And under such bilinear form, there is this key property that essentially I can move this B operator from one operator to the other at the price of replacing it with B dual. This will be the main engine of this method. And we will use another slide of slightly technical observations, but we will use these bilinear forms between Q functions, and the integration contour will go around all their poles. And I just want to discuss if these integrals really converge. So usually the convergence depends on the asymptotics of the Q functions and therefore on the charges, such as the scaling dimension of the operators. And we would like to define these integrals as analytic continuation from some region where there is good convergence. And we find a very efficient way to do this, which is to evaluate the integral by poles. And then we use a sort of zeta regularization to evaluate the tails summing infinitely many poles. And this is actually very fast to evaluate numerically. This is important because in the end, we claim that these bilinear forms are building blocks for correlators. And in practice, one might be worried about computing these residues, but this comes almost for free from the solutions of the TQ equation through this matrix omega. And through this regularization, we see that these bilinear forms are always finite when we consider two different states. When we consider the same state or states with the same scaling dimension, there are some divergences. It's divergent, but this divergence is physical, as I'll say in the next slide. So, and also we find that there is only a finite number or a finite basis of independent measures that we can use here that gives really independent results. And the number of elements of this basis is equal to the length of the spin chain. So now comes the heart of this argument. We'll consider two different states, A and B, where A is represented by the standard Q functions and B by the dual Q functions. Each satisfies their own finite difference equation. And these operators have some labels A, B, because I remind you that they contain the integrals of motion. And because of this adjointance key property I introduced before, there is this crucial equation. This is valid because I can annihilate QA with BA acting on the right, and BB I can move it on the left and annihilate Q dual. And if I expand this finite difference operator, this becomes a relation for the difference of the integrals of motion, which is a very important indicator because it's different from zero if and only if the states are different. And this, in fact, is more than one relation because I can pair different indices of the Q functions. This is 16 possibilities. I can use these J different measures, other J possibilities. So I get a linear system where the matrix of coefficients is built in terms of the Q functions. And if the two states are different, there should be a non-zero solution for this difference. And therefore, all the minors extracted from the matrix that have the same size as the number of integrals of motion should vanish. And the claim is that this relation is this orthogonality in terms of Q functions. And these minor determinants are proportional to the scalar product. So if we look at the diagonal case, as I said before, this right-hand side essentially diverges for almost all minors, but also the left-hand side diverges, because if we use the natural conformal invariant scalar product of the spin chain, if we apply it to CFT wave function with the same delta, there is actually a divergence. And of course, it would be interesting to regularize away from this, for example, introducing different twists for the two states and find a precise match. And from this, for this, probably we need the input from the operatorial approach. And we can also compute some prototypes of observables. And one class is some expectation value of some particular operators, expectation value in the same state, which are obtained as the variation of one of the integrals of motion with respect to any parameter of the system, which could be, for example, inhomogeneities or the coupling constant. And roughly, these are given by a sort of two-point function, which is modified by a different graph in the middle. And this is what is interesting is that in this family, there is a particular a particular case of three-point functions, which is on one hand extremely simple because it's the variation with respect to the coupling of the scaling dimension. But on the other hand, this is known to be an OPE coefficient between an operator, its conjugate, and the interacting part of the Lagrangian. And it gives us an example of the SOV expression for OPE coefficients. And to evaluate it, I will not explain the derivation, but essentially we look at this matrix M, but now in the diagonal case. And as I said before, almost all these minors are divergent, but actually because of a miracle that depends on the quantization condition, there is precisely one that is finite. And this variation of the integrals of motion with respect to the coupling is a null eigenvector of this finite minor. And this equation has a unique solution because in general, we find that this matrix has precisely one null eigenvector. And also the normalization is essentially fixed by the fact that one of the components of phi is the coupling constant itself. And through this, we can rewrite this OPE coefficient as a ratio of subdeterminants extracted from M. And this is interesting because before we had examples of SOV type formulas only involving essentially one variable and single integrals over the Q functions. And here we start to see this structure of determinant expected from SOV. And I don't have time to explain it, but using functional arguments coming in particular from this nice paper of Caetano and Komatsu is also possible to make progress towards the computation of the G function in separated variables. And we did this for the fishnet model. And as a last comment of this part, we can think of trying to do the same for n equals 4, this functional method. And surprisingly, many things seem to generalize nicely. So it's expected, for example, that the poles will open up and become counts with the position depending on the Hooft coupling. But apart from this, we expect that these bilinear forms are just defined by some integrals going around all the cuts, and they can be computed efficiently numerically, regularized in exactly the same way. And also, 4 of the Q functions satisfy a fourth order difference equation. And we still have these key properties that we had before, which was the engine of this method, if we identify correctly these Q functions and dual Q functions. The main difference that we expect is that now this n equals 4 has an infinite number of integrals of motion. And this is because it should be equivalent to a sigma model, and we expect infinite size determinants in the SOV expression, such as the one seen in a Sinch-Gordon model. And the main challenge is to find a good basis of these integrals of motion, which would be complete, linearly independent, and at the same time good for numerical evaluation and truncate into finite size determinants at weak coupling. So to summarize this part, we essentially start to see the fabrics of SOV in this fishnet theory, and it would be really useful to have operatorial tools to sew them together into correlation functions. And also, I repeat that it should be possible to apply this functional approach directly to n equals 4 super M mills, and this would probably be useful for linking the QSC and the G function. So now I move to the second part of the talk, which is work done with Nikolai Gromov, Julius, and Michelangelo Preti. And so in addition to integrability, there is another very powerful non-perturbative method, which is the conformal bootstrap. And in recent years, we've learned that the constraints that come from decomposing in the operator products expansion of a 4-point function in 2 different channels are extremely powerful. They can be used to explore the space of consistency of T's. And in many cases, one can zoom on a particular theory and use these equations to compute its conformal data. So these are famous results for the 3D Ising model. And we want to ask what we can achieve by using the conformal bootstrap, but using the fact that through integrability, we know the spectrum. And this idea was used in studying models of 2D critical statistical mechanical models. And this, in this case, it was used to check some conjectures for the analytic formula for the OPE coefficients. And in a similar way, we can try to use this formula to formulate some predictions for integrability, and maybe in some cases even to compute things that maybe are out of reach for integrability. And but there is a known obstacle if we want to apply this logic to 4-point functions of local operators, namely that in a planar 4-point function, there is also a contribution from subleading contributions at one over n order coming from double traces. And to avoid this complication, we start by considering a setup where there is no such effect. So we study some correlators that are insertions of operators of an infinite Wilson line embedded in n equals 4 superior mills. So the operators are built as usual out of the fields of the theory. And the gauge connection is the supersymmetric combination of the gluon and one of the scalars of the theory, where I consider, so this scalar has a fixed orientation out of 6 possibilities along the line, which will be denoted as phi parallel. And these are interesting observables because they represent some infinitesimal bumps in the Wilson line, and conceptually, they should contain information about Wilson loops of arbitrary shapes. And crucially, these correlators satisfy the axioms of 1D CFT, and we will use this one-dimensional version of the conformal bootstrap. And I want also to mention that there is a dual strong coupling description in terms of a QFT on ADS2, but we will try to reach the finite coupling region through integrability. So the symmetries of these systems are, as I said, this 1D conformal symmetry. It's generated by dilatation, translations, and spatial conformal transformation along this line. And then there are some global symmetries that come from the embedding in 4 dimensions. So we have rotations around this line. And then there is because we picked one particular scalar on the line, we have an R symmetry of rotations among the remaining 5 orthogonal scalars. These symmetries are all embedded into a super conformal group. And for this talk, it's important to name the 2 simplest protected multiplets. So the first has as primary one of these orthogonal operators and as protected dimension 1. And the second multiplet is called B2 and has protected dimension 2. And I also mentioned that the simplest, lightest non-protected operator instead starts at coupling with phi parallel. And so we'll consider the simplest 4-point function of the theory, which is built by 4 of these supersymmetric orthogonal scalars, all with the same orientation. And this 4-point function is written in terms of a function of the cross ratio of the 4 points. And there is a crossing equation. It can be obtained by mapping the line to a circle through a 4-dimensional conformal transformation, and then relabeling 1, 2, 3, 4 into 4, 1, 2, 3 due to cyclic symmetry. And then the cross ratio goes from chi to 1 minus chi. And to write the OPE, it's very convenient to take into account the supersymmetric degeneracies. And we do this with the formalism of this beautiful paper. So we rewrite the amplitude in terms of a function f of the cross ratio, which satisfies the crossing in this form. And they showed that this is the form of the operator products expansion, where the operators flowing. So here we're fusing the channels 1, 2, and 3, 4. The operators flowing can be the identity. This is supersymmetric multiplet B2. And then there is a tower of infinitely many operators with non-trivial dimensions, which all have to be singlets of this global symmetry SO5 cross SO3. And here in this expansion appear the OP coefficient and also the super conformal blocks fixed completely by symmetries, where the blocks for these unknown states is an explicit function of their dimension. And they also showed that this OP coefficient that couples to B2, while it's a function of the coupling, can be fixed explicitly by studying a related topological observable. We will use this result. And this is the form of the conformal bootstrap constraint, which comes combining the OPE and crossing symmetry. So here I introduce these G's, which are combination of the block and the crossed block. And I want to split this formula in two pieces. The first piece is explicitly known as a function of the cross ratio and the 't Hooft coupling, and is a combination of these 1 plus B2 blocks. And the other piece contain all the unknowns, the spectrum of non-protected operator and their OPE coefficients. And so through the bootstrap, it's already possible to obtain very nice results even without integrability. So studying the multi-correlator bootstrap, Meneghelli and Ferrero were able to obtain analytically result of strong coupling up to 4 loops. And we will hear about it in Pietro's talk on Thursday. So now the integrability comes in the calculation of the spectrum of all these exchanged operators. And these are a particular case of a setup of operators inserted on a cusp of this supersymmetric line, which is known to be integrable. And after years of study, a quantum spectral curve equation for these operators was derived, which is similar to the one described in the standard spectrum, but with different analyticity conditions for the Q function. And we want to find the operators that, that as I said, are singlets of the unbroken symmetries of the setup when we take this cusp to be a straight line. And these are some examples. So the first lightest operator starts with classical dimension 1. Then there are 2 operators of classical dimension 2, which are built out of these neutral combinations of scalars, and then the number increases. And they're a bit enigmatic because they have the same quantum numbers of the vacuum, but it was found in this paper, one should just find them as some excited states of the same QSC equations that describe the cusp without insertions. And the challenge in actually computing them is the numerical method to solve the QSC requires to have a very good initial condition close to a physical state for convergence. And it was very convenient for us that these neutral states, while they do not satisfy, at least there's no reason they should satisfy asymptotic beta equations, they satisfy some one loop beta equations. This was shown for a subset of the states in this paper, and we found that it's true for all of them. And we rewrote these equations into a more efficient set of one loop Baxter equation. These were first found by Julius for a subset of these states, and we generalized it. And this is very efficient to jumpstart the QSC, and then we can track the coupling dependence. And with this, so here is a plot of, for example, 35 of these states flying in the OP as a function of the coupling. And so we have taken the low-lying states in order, but in the high part of the spectrum, some are missing. So there should be many more states starting here, but we just didn't compute them all. The observations I want to make on this spectrum is that it's very regular at weak and strong coupling. At strong coupling, the states group together into some trajectories and go to some interior dimensions. And in the middle region, it's complicated with level crossings and a high density of states. So now that conceptually we have the spectrum, we want to try to use this crossing equation to study the OPE coefficients. And there are 2 problems to solve. One is that there is an infinite sum of the number of states here. And in practice, we can only compute a finite number of them. And then this is a equation for functions of the cross ratio. So we need to understand what to do about it. And I'll briefly review the method that was used for these 2D statistical models. And this method was to essentially truncate the sum to a finite number of states and sample the equation at some choices of values for the cross ratio. And then this gives a linear system, allows to compute the OPE coefficients. And then the idea is to do statistics over different choices of the sampling points to get estimates for the error. And while this worked very well in this setup, we find that for us, it gives rather bad precision. And we think this is a feature of our spectrum, which in the middle coupling region has a density of states that increases very rapidly. And but it worked well, for example, if we go at very weak coupling or very strong coupling when the spectrum becomes more regular. But another idea is then, rather than sample the equation at some points, we can try to act on it with some linear functionals. Linear functional on the space of functions of the cross ratio, which formally can be written as an infinite superposition of derivatives evaluated at some point. For example, this point where the OPE converges the fastest. And admitting that it's allowed to exchange the action of this functional with this infinite sum. And for this, there are some rigorous arguments in the bootstrap literature. Then we can transform this bootstrap equation into this scalar equation. And the game is trying to find functionals with good properties that allow us to extract information on C. And to illustrate this idea in an extreme case. So some dream could be to find some functionals that essentially, when we apply it on the blocks, they give 0 for exactly almost all states of the spectrum except one. Then we would have that almost all terms here drop out. And we have just 2 terms, and we would find an analytic solution for the OPE coefficients in terms of the action of these functionals on the identity block. But this is unreasonable. Such functionals are known only for free theories. And it's an open question if these explicit analytic functionals can be used for us, useful in our context. But more pragmatically, we can try numerically to find functionals with some useful properties. For example, functionals that are small, above a certain threshold in the scaling dimension. And we can find such functionals numerically, and this would give a controllable way to do this truncation on the high levels in the spectrum, which already gives good results compatible with the ones I will present later. And this method has the advantage that it works also for non-unitary theories. But then the method that worked the best in the end was to instead look for functional with some positivity properties. So instead we impose that the functional is positive after some threshold. And this combined with the fact that in our theory, the OPE coefficients are real. And so their square are positive, allows to derive some inequalities and use these inequalities to carve out the theory space. This is exactly as was described in Yifei's talk about the S-matrix bootstrap, and allows to find some bounds on the allowed conformal data. So to impose these kind of conditions, we need to use some numerical techniques called semi-definite programming. And luckily they were introduced in the bootstrap, and some powerful numerical packages are available called SDPB. And essentially the only approximation in this method is that we represent a function as some finite vectors, finite combination of derivative. But the beauty is that it can be proved rigorously that increasing the number of derivatives, the bounds can only get more constraining and can only get better. So these are rigorous bounds. And so here we start by applying a known algorithm of the numerical bootstrap to obtain bounds for the OPE coefficients of the lightest operator, but we adapt it to the situation where we know the spectrum. So the algorithm is, we should look for a functional that takes the value 1 on the block for the lightest operator. Here we give the information on delta 1. Then it should be positive after a threshold, and we choose it to be the position of the next operator, delta 2. And among these functions, we look for the one that maximizes its value on the identity block. And this gives this equation where this positive contribution is comes from all the other states. And essentially from this, we obtain an upper bound on the OPE coefficient. And without going into detail, you can believe that one can tweak the algorithm, changing it a little such that it gives now a lower bound, also looking for another functional. And for example, here, if we take the coupling to be half and 20 derivatives. This is the action of these functionals on the blocks as a function of delta. And what I want to remark is that even though we just impose that they're positive in this region, they're actually very small. And this suggests that even though we just input information on delta 1 and delta 2, actually the details on the rest of the spectrum do not matter too much for the precision of the result. And so finding these functionals for different points of values of the coupling, we can construct this plot for the OPE coefficient as a value of the coupling, which almost look like a line, but this is the field region between these two bounds. So you see that it's a very narrow region, and already it matches very well with the strong coupling prediction of Pietro and Carlo, and also with weak coupling results. And in this other plot, we see how the error evolves if we increase the number of derivatives. And so the error is small, and we can do an extrapolation to infinitely many derivatives, where we see that the error goes to 0 at very weak and very strong coupling, but it actually doesn't go to 0 in the middle region. There is some asymptotic width that we cannot go beyond. And we have also tried more experiments. So other experiments involve, for example, using the OPE coefficient for the next two states as parameters. We do this by putting them together with the identity block, and then we rerun essentially the same algorithm. And this basically gives now some upper and lower bounds that depends on these numbers as parameters. And we can ask, when do these bounds become inconsistent, either with the previous bound, or maybe we can find that the lower bound is higher than the upper bound and exclude some regions. And with this, we can find some allowed islands for the next two OPE coefficients that also shrinks as we increase the number of derivatives. Okay, so in conclusion, with this method of combining integrability with a conformal bootstrap, we found some rather accurate data for the OPE coefficients of the lattice operator as a function of the coupling constant for all values. And it's a very nice result. On the other hand, we would like to understand is if this, so we found this asymptotic resolution that we cannot go beyond. And the question is if there is a way to harvest more information from integrability, input more about the other states on the spectrum, and a way maybe to shrink these bounds to 0. And another question is if it's possible to obtain precise bounds for the next OPE coefficients, and maybe underline the conceptual question is if there is any hope that using the bootstrap theory is determined completely by the knowledge of the spectrum. And another question is what we can achieve analytically with these methods. And so there are various analytical methods for the bootstrap, for example, that will be discussed by Pietro on Thursday. And maybe another very important question is if we can work around this problem of double traces in some way and learn how to study with these methods the OPE coefficients of the local theory. Okay, with this, thank you very much for your attention.
Yeah, thanks for the talk. So since I've got the microphone, maybe I can pose the first question. One thing here in the end that springs to mind, there was this high spin analytical bootstrap activity by Andrea Cavaglià for some other people. Like, I mean, since we got a lot of mileage out of high spin things in BES and so on in the old days, do you think there's some way of using that in this context?
So concretely, I haven't thought about it, but the hope is, yes. Well, I can mention that in this analytical bootstrap, there's a lot of consideration about complex spin, for example. And for this analytic continuation in spin can be done very efficiently with a quantum spectral curve, for example, for the spectrum. So it would be very nice to explore these connections, but we haven't done it. Yeah.
Okay, so that was my first one. The other one is coming back to that class of 3-point functions. I mean, the fact that you get the Lagrangian down from the action by differentiation in the coupling constant essentially says that that kind of correlator is the same as a 2-point function, doesn't it?
Yeah, but
so what's, I mean, the question is like, what's your hope to get away from there? Have there been advances in trying to address other operators?
So, well, that correlator itself is not interesting, because we could just compute it by differentiating the spectrum. But the point is that on the other side, we have an expression where there are the Q functions only for one value of the coupling. And this expression should have some universality and appear also in other correlators. For example, essentially the determinant in the denominator of that expression should represent the norm of the state in separated variables. And that should appear from examples. We expect that it appears in the determinants of other 3-point functions, in the denominator of other 3-point functions as well.
Okay, but maybe one more. In your nice picture with the 3 ends. So what sits in the middle? I mean, there was some mysterious zone, which, I mean, you just imagine that goes smoothly and there's no new object that...
I mean, it depends on the particular 3-point function that you look at, but essentially the point is that you can always find a way to cut it such that externally we always find these diagrams or analogs. And then in the middle, you always have the same thing. It doesn't change with the loop order, what you have in the middle. It's some 3 graph.
That is supposed to be holding away from the fishnet? I mean, in n equals 4, you would expect something of the type? Or,
I don't know how to interpret this in n equals. Also, the CFT wave function doesn't have a generalization that I know.
Yeah, let's hope that something is going to come about. Okay, more questions from the... Okay.
Okay, thanks, Andrea. So my question is about level crossing. So the first question is if in the 1D example you showed, of course. So yeah, if you go to the, yeah, thanks. So the first question is if things really cross, if you can really numerically, for example, with a quantum spectral curve, zoom in near a crossing, and if they really cross or they avoid each other somehow. That's the first question. And the second question is this level crossing could be related with the fact that you had an error that didn't shrink to 0 when the number of derivatives in the functional, on the functional went to infinity. Because it seems to me that the bump in the error is close to the point where the first crossing happens. But please.
Sorry, can you repeat the second part? I understood the question about level crossing if it's really there, but not the second part. I cannot hear you.
Okay, thanks. The host didn't allow me to unmute myself. So now it was just if the thing, the error having a staying finite had anything to do with level crossing, or you think it's a completely unrelated issue? That's the second question.
I didn't think about. I didn't think there could be a connection, but would be happy to discuss it if you think it's related.
Yes, but the first question remains. Yeah,
it looks like they really cross. And
they really
also,
cross. Okay.
Yeah, in integrable system, usually you expect level crossing.
Okay, thanks. Yeah, I understand. I agree with the Cavaglià complaint. Okay, 4.2. Thanks.
Yes, yeah, that's a good point. So we use only information on the first 2 states for this result.
Yeah, and also they only cross in the delta. There are many other consort charges where they don't cross, right? It's, if you take second consort charge, they will cross in a different place.
Can we get Volodya Kazakov to...
Hi, Volodya, do you want to ask a question?
Yes, yes. I have two quick questions. First of all, can you apply your methods of the second half of the talk to the quantities of the first half of the talk, namely to compute the 3-point functions or 4-point functions in fishnet in the situation when it's not non-unitary? Can one do something like that?
Yeah, then one can try with this other method of constructing functions that are very small after a certain level. We haven't find a way to making it optimal such that it gives the same precision for all the OPE coefficients. So it seems to work well for the lightest one. So one could try with that for non-unitary theories.
Yeah, it would be very interesting because we had some project abandoned with Burkhard Eden and João Caetano about this specific Feynman diagram in fishnet, which is the lowest order 3-point function, but we couldn't make sense out of it. Would be interesting to try with your method. And the second question, if you can try also to study the Coulomb phase of n equals 4, and as far as I heard, there are some signs of integrability there. Just independently on it, one can write equations on the 1-point functions also. Could you do something like that in principle by these methods?
You mean using some kind of bulk defect mixed bootstrap equations and like
probably
bulk data and defect?
I remember this paper of Shaposhnikov and Karananas, where they had some relations similar to bootstrap for 1-point functions. That would be also great. No,
Thanks.
It's a great method that you invented.
It would be great to look at it. Yeah.
That should be very useful. Thank you.
Thanks.
Do we have more questions on the net, or when Kolya still has got his hand up?
Who? Sorry.
There's still
Kolya, do you want to ask a question?
Well, it's my own hand, but I just want to emphasize, maybe it didn't come through, that actually for our result, which Andrea showed with this very narrow bound, we only use 2 states so far. And the reason is that the standard methods of numerical bootstrap at the moment only allow this. So it requires further modifications to take into account all our 35 lovely states. So hopefully this will improve precision. But we don't know yet. Thanks.
So do we have questions in the audience?
Yes, so I was curious about the mixing problem, because at strong coupling, obviously there's the issue of degeneracy in finding the CFT data. And since here there's a coupling dependency, I can imagine that lower down in the spectrum it isn't a problem, but is there a certain kind of minimum weight where the precision of the numerical bootstrap doesn't allow you to differentiate the different operators?
Yeah, so so this result we have is only for the lightest one. And we can try to study more states using for this method of these functions that are small after some point. And with this, you can study some states, but at least with the method we tried so far, the precision gets worse if you go higher in the spectrum. And also, as you said, so of course, if there are states that are very close, it's increasingly difficult and you get some precision problem there. But maybe there are some better algorithms to deal with that.
Okay, thank you.
I just comment on the same. So Andrea had this picture for C2, C3, where you if you can show it, Andrea.
Yeah, there's one second.
So that you see, so this allowed domain is very narrow, but it's stretched in one direction. And the reason is exactly because the states are almost degenerate. So if they were a bit further apart, it would be just a tiny spot on the graph. But because they're so close to each other, we also have this problem of actually pointing out which of this C2, C3 corresponds to. Exactly. So it's a bit stretched in one direction, which is annoying. Otherwise, it would be much better, of course.
There was someone else. Oh, hello.
So just to confirm, in the beginning, you mentioned that you also used the one of the structure constants coming from some topological localization computation. So you used that and two states of the spectrum. Is that right? Okay, thanks.
Then we had somebody behind there.
Hi, thanks. And yeah, thanks, Andrea, for the talk. I was wondering about the precision in the determination of the spectrum in the plot that you were showing with all the states, whether it's the same at weak and strong coupling, because it seems like you're truncating at some value of the coupling, of course, but the states are not really reaching the asymptote. So I was wondering whether like strong coupling it is less precise or something like that.
So in principle, it's known how to use this method, and if in terms of just the problem is computational time, but you can push the precision to arbitrary values if you want to. But then it's also true that with current methods to solve this equation, the strong coupling region is more difficult. So they take longer to converge. You need to use more parameters, so it's more expensive to compute a strong coupling.
Okay, thank you.